and welcome to today's class. Still some people to join, but we will start anyhow because it's already 7:40 past. So we were talking about the various kinematics parameters last time, and we saw the general definition in vector form, like position vector, displacement vector, velocity, both instantaneous and average, and then acceleration, both instantaneous and average. Then we saw how to reduce these vector definitions in the scalar notation for one-dimensional motion, where position simply becomes a coordinate, right? And displacement becomes the change in the coordinate and those things. So we will continue from that onwards today. So we will concentrate on motion along a straight line, or what is called one-dimensional kinematics, for a bit of time, and then we will come back to the general 2- and 3-dimensional kinematics today. I don't know, maybe some people are not able to join because of internet issues with the heavy rainfall. Anyhow, so let's begin. So we'll go back to kinematics in one dimension, or motion along a straight line. What is called one-dimensional motion, or in very short form 1D motion. So here we saw that position can be just expressed as a coordinate, assuming that the motion is along the x-axis. If we, for whatever reason, select the axis as something else like the y or z axis, then that particular coordinate will become position. So displacement S becomes the change in position, or x2 minus x1, whatever, final minus initial position. Okay, velocity comes such that instantaneous velocity is rate of change of position, which is the same thing as rate of change of displacement. And average velocity becomes displacement divided by time, or delta x by delta t, or also express it as x2 minus x1 upon t2 minus t1. And acceleration, A becomes dv by dt. And average acceleration becomes delta v by delta t, or t2 minus v1 upon t2 minus t1. Now we'll see some additional aspects of this today. But before that, we understand that all these quantities, all parameters here are with an algebraic sign. That is positive or negative, which indicates the direction. You might ask that how is position going to have direction? Displacement, velocity, acceleration, all this, yes, we understand it has direction. So position is also direction in terms of with respect to the origin, which direction the position is in. Is it towards the positive direction, or is it towards the negative direction? So this is these are the basics that we understood last time. Okay. Now today we will also see that these quantities which we have defined in terms of derivatives, or rate of change with respect to time, like instantaneous velocity, instantaneous acceleration, etc. We can also define the reverse of that equation in terms of integration. So first thing we'll see here is that the relationship between displacement and velocity, or position and velocity, is like this, that we say that velocity is rate of change of displacement. Okay. So instantaneous velocity equals the instantaneous rate of change of displacement or position, they are one and the same thing, with respect to time. So that is the definition. So that now also indicates the reverse of this, that displacement will be integration of velocity with respect to time for whatever time interval t1 to t2. So this now automatically it implies that displacement in a time interval t1 to t2 equals to the integration of velocity with respect to time from t equal to t1 to t equal to, or another way of expressing the same thing is that dx by dt is equal to v. That means delta x is equal to integration of v dt from t1 to t2, or x2 minus x1 is equal to integration of v dt from t equal to t1, t equal to t2. So where this idea basically comes from is that it is coming from the definition of integration, that it is the reverse process of differentiation. Right now, so it's very clear to understand here that yes.
Sir, can you explain this again?
Yeah, I am in the process of explaining again. So if we are saying that v is equal to ds by dt, that means v is the derivative of s with respect to time. So what is the reverse of this statement? It means that s is the antiderivative of v. So s is equal to integration v dt because v is equal to ds by dt. That's the simple logic of that. Okay? So just make a note of this now. With examples, you will understand this better.
Sir, can you scroll a little up?
Yeah, beta. So these parameters that we have written above and the relationships we have seen in the last lecture up to that average acceleration. Now we are starting from that point onwards. Okay, so another thing that it explains about the relationship between displacement and velocity or position and velocity is that if you visualize the velocity time graph, okay, what is the displacement in a certain time interval from that graph, it's going to be area under the graph or area under the curve. So suppose my instantaneous velocity versus time is varying according to this curve. So this is velocity as a function of time. And suppose this time is t1 over here, and this time is t2 over here. Then what represents the displacement in this time interval? It is this area. So this area, which is basically the integration of v dt from time t1 to t2, that represents the displacement or the change in position from time t1 to t2. So it is area under the graph that represents this quantity. So what we have done with the integration over here, that you understand visually from the graph below. Okay, so next let us move on to the relationship between acceleration and velocity. Instantaneous acceleration and instantaneous velocity. The relationship is
Can you scroll up a bit for a second?
okay.
So done.
Okay. Yeah, so now coming to the relationship between acceleration and velocity. So the inverse of this relation now is that we just cross multiply this. We have this, okay, cross multiply the dt. So once again, integration of dv is on the other side integration of e dt. Okay. So change in velocity delta v in a certain interval of time will be integration of acceleration in that particular interval of time. So change in velocity delta v or v2 minus v1 in a certain time interval equals to the integration of acceleration with respect to time from the initial time t1 to the final time t2. So again, this also has a graphical meaning. That is, if you draw the acceleration versus time graph, then the area under the graph will represent the change in velocity.
Sir, how can we integrate only dv?
Like you integrate only dx, beta. Like a constant into dx integration is what? A linear function, no? So that constant is 1. Understood, huh?
Yes.
Hmm? So actually, this is how this step comes. Okay. Indefinite integration of dx would be what? X plus c. So like that, indefinite integration of dx from x1 to x2 would be equal to x2 minus x1. Okay. That is basically a change in x, delta x. So like that, indefinite integration of dv or definite integration of dv from some initial position to final position or initial velocity to final velocity would be v2 minus v1, which is your delta v. Got it now?
Yes, sir.
Okay. So let's see this with some examples. So for example, suppose we have a particle moves along the x-axis, starting with an initial velocity of plus 5 meters per second at t equal to 0 from the position x naught equal to, let's say, plus 1 meter, and has a variable acceleration. That means whatever force must be acting on the particle is changing with time. So it's giving it a variable acceleration. Now that acceleration is given by, suppose, plus 2t, where the acceleration is in meters per second square and t is in seconds. It's time in seconds. Okay. So we want to find, first of all, velocity, that is instantaneous velocity, as a function of time. And from that, the value of instantaneous velocity at t equal to 1 second, t equal to 5 seconds. And then we want to find the displacement s from t equal to 1 second to t equal to 5 seconds. This particular interval of time, what is the displacement? We want to calculate this. Okay. So you will see that this is that typical kind of situation where we cannot use the standard equations that we've learned in 9th before, that v equal to u plus at and s equal to ut plus half at squared. Because the moment you think about those equations, you'll realize they won't work, because what will you substitute a as? In that time interval that we are talking about from 1 to 5 seconds or whatever, your a is varying by a large amount. Your acceleration is 2 initially. Okay. Then at 1 second, it is becoming 4. At 2 seconds, it's becoming 6, like that. So it's varying very rapidly. So there is no point of thinking about those equations, because those equations are only valid when acceleration is uniform. So that means we have to go back to the fundamental concept here. We can't use the specific equations for uniform acceleration. So what is the fundamental concept, relating these quantities is these concepts. This is the relation between acceleration and velocity. The next one is the relation between velocity, or the earlier one was the relation between velocity and displacement. So we have to use those fundamental definitions or those fundamental concepts. Okay. So just give this a try. We'll discuss in a minute. So it's just like a calculus problem. If I had given you velocity as a function of time, you know that acceleration would come by differentiating the velocity, because that's how it's defined. A is dv by dt. So now instead what is happening? You would use this equation if v was given and a was asked. But here is the reverse. Okay. E is given and v is asked. So v is going to come from what? Integration. It's that kind of concept. Okay, very good. Adinath and Akshat, your answers are correct. Okay. So let's understand over here that, so the first part, now I'll elaborate that there are actually first part to find velocity as a function of time. We have two options. One is we can go with indefinite integration. Okay, so we have acceleration is equal to 2 plus 2t. Okay. And we know that additionally that at t equal to 0, the initial velocity was given as how much? 5, was it? Yeah. Just a moment. Okay, so we can use this relation that dv by dt is equal to 2 plus 2t. So that means so one is we can do an indefinite integration. So that means v is equal to 2t plus t square plus some constant of integration. Now, how we'll remove the constant of integration? Now use this over here, like I've told you before, that such that at t equal to 0, here we don't know the constant of integration, so we'll use this. At t equal to 0, our u should be equal to plus 5. So 5 should be equal to 0 plus c. So that means the value of the constant is 5. So that tells me now the complete answer that v as a function of time is 5 plus 2t. It doesn't matter what order we write it, we can write it. Okay. So now you see that you can also check that this matches the information that is given. Okay. So this is velocity as a function of time. And you can just check over here that put t equal to 0, you'll get the velocity as plus 5. So that's correct. And differentiate this. So you will get the acceleration as 2 plus 2t. So that's also correct. So that means I've not made any error in my calculation. Okay, because it's when I reverse calculate, it's giving me the condition that is given in the question. So there's no problem. Okay. This is one option. Okay, this is using indefinite integration. I also have a second option. I can also use definite integration. So I have that option also. Okay. So what I can do is once I've got this step that TV is equal to 2 plus 2t dt. Next step on both sides, I can do a definite integration. So I can put limits. Okay. But the limits will be such that this side I will integrate from t equal to 0 to some instantaneous time t. So the upper limit is actually a variable. Okay. And on this side, my initial velocity at t equal to 0 is known. So it's 5. Okay. But at time t, the velocity is v, which is unknown. So we do a definite integration where lower limit is the start of the motion. That is t equal to 0, u equal to 5 meters per second. But the upper limit is t equal to t. That is a variable time. And t equal to v. That is the instantaneous velocity.
So can you once again explain how we got phi as the constant?
Yeah, you put time as 0. You use this condition that is given, no? That at t equal to 0, the value of initial velocity was 5, no? So in that equation, you put the value on the left hand side, put v as 5, but at what time? When t is 0. So you get that constant value as 5. Got it, no?
Yes, sir.
Okay, so anyhow, let's now look at this definite integration method also. So in this is what we are doing. Okay, on that side. Okay, so left hand side we have v, but the limits are from 5 to the unknown velocity v. And right hand side the antiderivative is 2t plus t square. But the limits are from t equal to 0 to t equal to t. The left hand side becomes v minus 5. Right hand side becomes 2t plus t square. That's the upper limit, minus 0. That's the lower limit. That gives you the same relation, that v is equal to 5 plus 2t plus t square. So it's really up to us which of the two methods we want to use for this instantaneous velocity problem. Okay, we can go with the indefinite integration and eliminate the constant using the given condition that at t equal to 0. So this process, what we have done is we are eliminating the unknown constant c using the initial velocities value. So as you can see, this is nothing but application of calculus. Okay, one-dimensional kinematics is completely about application of calculus, and general 2 or 3-dimensional kinematics is application of vectors and calculus, both the things put together. So if you are clear with your concepts of calculus and vectors, you should not have too much difficulty with kinematics at all. You will find it a very interesting subject. Okay, so that's the first part done. We've got velocity as a function of time. Now we want to find the value of velocity at 1 and 5 seconds. So that's just a matter of substitution. We can just, so this is the answer to our first part. Now we want to find the velocity at a particular instant. We want to find v at t equal to 1 second. So you can see that, let's say that is v1. That is, in this you substitute the value of t as 1. Okay, so that becomes how much? Equal to 8 in meters per second. You again want to find the value of velocity at 5 seconds or whatever, you find it as plus 25 plus 10, 35 plus 5, 40. You can see the velocity is increased from 8 to 40 by the time the time is 5 seconds. So not 2 but 5. So that's done. If now next thing is we want to find displacement in a certain time interval from 1 to 5 seconds or whatever. So for that we have to go back to the fundamental relationship between instantaneous velocity and displacement. Okay. Okay, so now next thing, displacement is integration of velocity. This is the displacement in time interval. T1 to T2. That's the relationship. So here, displacement from 1 to 5 seconds, we have to calculate that, will be integration of velocity from t equal to 1, t equal to 5 seconds. Okay. So now just substitute this instantaneous velocity now. So it is 5 plus 2t plus t square. But with the limits t equal to 1 second to t equal to 5 seconds. So this is 5t plus t square plus t cube by 3. That is the antiderivative. Okay. I'm not writing the constant because it will anyway cancel out. Now you have to put these limits. So the upper limit is how much? It's 25 plus 25, 50 plus 125 by 3. That is 50 plus 41.67. So that is 91.67, right? Upper limit will be 91.67 minus lower limit will become how much? 5 plus 1 plus 1 by 3. So 6.33. So that will become 85.34. And in the positive direction, that is the displacement from 1 to 5 seconds. So this is the very important aspect over here. Application of calculus.
What about the constancy?
Which constant in which part, beta?
In the third part, sir.
Third part, beta, we're doing definite integration. So the constant is not there. It gets, remember, in definite integration, it's a definite value na, when you put the limits.
Yes, sir. Yes, sir.
Got it? No? So basically, you visualize now what you're doing is in your velocity time graph, you're finding the area under the graph from the specific time t equal to 1 second to the specific time t equal to 5 seconds. So hope this point is clear. Na? After the first part, I've not used indefinite integration anywhere. No? I've used definite integration. So that's why the constant of integration is not coming. Okay, so hope this question was fully clear. Now, one more thing we'll notice here that since acceleration is dv by dt and instantaneous velocity is ds by dt or dx by dt, therefore we can also say that acceleration's relationship with displacement of position is that it is second derivative. That's one important thing. So for example, suppose we have that displacement is equal to something like this. So here displacement is in meters and t is in seconds. So find instantaneous velocity and instantaneous acceleration as functions of time, and then find their values. It's not displacement, this is position. So this is for a 1D motion, obviously along x-axis. Okay, and then find their values at say t equal to
So what
1
it is,
second.
sign in the bracket k by 6.
Pi by 6, pi. Pi by 6 into t. Got it now? Okay. So let's work this question out quickly. So now there's a reverse question. This is where we'll use differentiation because here position is given. We have to find velocity, which will come by differentiating that. And then we have to find acceleration, which will come by again differentiating that. What happened?
So that A is equal to d square by s, it will be dt square, na?
Yeah, sorry, my mistake. In the denominator, it should be d2s by dt square. Correct. Please make this correction, everyone. That's second derivative. For a differentiation, remember you have to use chain rule, no? Because it is not sine t, it is sine of some constant into t. So like remember how you did differentiation of sine 2x. It became cos 2x into 2, right? It was 2 cos 2x. So like that, okay. Here it's differentiation of sine of some constant into t.
So, please out of the bracket.
Okay, so people, I'm not getting answers from you, so I'm just thinking, okay, so let's go over this once again. We know that differentiation of sine x is cos x. So therefore, differentiation of sine of, let's say, some constant into x, that will become what? It will become a cos x like this. This is by chain rule. Put ax as z. So sine ax becomes sine z. Okay. So then you apply that chain rule. So likewise, what will be differentiation of sine of pi by 6 into t with respect to time? It will be pi by 6 into cos pi by 60. Because pi by 6 is a constant over here. That's how you'll get the first part. So you're differentiating with respect to time, this whole thing. 20 sine of a constant, which is pi by 6 in value, into time t. So the first step is that you take the 20 outside because that's a constant again. Then you differentiate this sine term. So its derivative is cos. Okay, but there's the pi by 6 multiplied by time. So also have to multiply it with pi by 6. So instantaneous velocity as a function of time is becoming 10 pi by 3 cos of pi by 6 t. This is your velocity, instantaneous velocity as a function of time. So this application of differentiation with chain rule is clear over here. It's something that you are very used to in calculus chapter, is that sometimes you can get confused with parametric terms here. So
So how can we cut with pi by 6? Pi by 6 is angle na here. Pi
No,
by 6.
actually pi by 6 will be in what we call radians per second, because the whole quantity pi by 6 into t is an angle. If you think in terms of dimensions, no? Sine or cos applies to what kind of quantity? A dimensionless quantity, which is expressed in radians. You understanding? No?
Yes, sir.
So the value of that constant is pi by 6, but the unit of that constant is not radians, it is radians per second. So when you multiply it with time in seconds, then you should get an angle in radians. I mean, see, pi is just a number, no? So like, it doesn't mean that every time there's pi, it is in radians.
Oh. So instead of it had been in degrees, we wouldn't have been able to cut na.
Sorry, come again.
If it would have been in degrees.
No, it is given as pi by 6, no? So that means when you substitute the value of time as something over there, you get an angle which is in radians, no? Okay, so the pi by 6 here, no, understand that it is a constant which is not in radians, it is in radians per second. So we cannot just express it in degrees. Okay. If it is some angle that we are talking about, then yes, an angle of pi by 6 radians is equivalent to 30 degrees. Okay. But here it is a
Yes.
constant which is having some different dimension, some different unit. It is in radians per second. So we cannot convert it like that to degrees per second. That constant has a specific value of 3.14 divided by 6. So if I convert it to degrees, it will give me something totally different. You know, when you are doing the differentiation and that constant comes outside, its value will not make sense if you converted it to degrees per second. Okay? It has to be left the way it is. Its value is pi by 6. Okay. So in this, the other thing you can take note of, now here you can understand, is that in this relation, for the given value of x, 20 sine pi by 6t, this quantity 20 is actually 20 meters, because x is in meters. Okay. And this quantity pi by 6 is actually pi by 6 radians per second. Now radian is what kind of quantity? It is a dimensionless quantity. It's a fraction, because angle in radian is defined as arc upon radius. Now if you express an angle in radians, it is just the ratio of two things expressed in the same unit. So it is unitless. Okay. Whereas when we convert it to degrees, it's not like it's unitless. So now when we write v as 20 into pi by 6 cos pi by 6t. Now in this quantity is in meters, this is in radians per second. So this becomes, the whole thing becomes in meters per second. So this expression, you can see the unit of this quantity here is in meters per second. This quantity, the whole thing is in radians, because it's pi by 6 radians per second into whatever time in seconds. Okay. So that's how we are getting that the velocity in meters per second is equal to this value. So you see the point now. If you change that pi radians to 180 degrees, you run into trouble with the unit of V. Okay. So that is why in this type of situation, we never do that. Okay. It's only in the specific case where we are converting an angle in radians to degrees, we use that relationship. But here it's not really conversion of an angle. That pi by 6 is actually a physical constant which has the dimension of per second, okay, or the dimension of per unit time. So Adinath, hope this point is clear here. No?
Yes, sir.
Yeah. So this velocity is value that we got here in the second part. This here, the velocity is such that it is in meters per second. And the time is in seconds. Rest are all constants. Okay, so we will come back to the V to calculate its value at all these in the second part. But before that, let's continue ahead and find the acceleration. So next thing, now acceleration is dv by dt, or that's the same thing as second derivative of x with respect to time. So acceleration here will be differentiation of this v that we've written above. So the same process repeats, but this time you're differentiating a cos function. So its derivative will be a minus sign. But again, while doing the differentiation, you will have to make use of chain rule, because that constant pi by 6 into t. So again, that kind of thing, that differentiation of cos is minus sign. So therefore, differentiation of, it's a constant a into x become minus a sine ax. That kind of application we use. So 10 pi by 3 comes outside, okay, into differentiation of cos is minus sine, but because it's pi by 6 into t inside, so there's a pi by 6 that comes outside also. So as you can see, this becomes say 5 pi square by 9 sine of, with a minus sign, of course. Okay. So minus 5 pi square by 9 sine of pi by 6 t. This is the instantaneous acceleration as a function of time. So the acceleration is in meters per second square. The time is once again in seconds. So in this expression, again, you can see that this term is in meters per second square. So this term here was basically at 10 pi by 3 into pi by 6. No? Now this pi by 6 was in radians per second, and this was in meters per second. Therefore, the whole thing is becoming in meters per second square. Whereas this quantity here, it is in radians. It is pi by 6 radians per second multiplied with time in seconds. Okay, so just make a note of this and then work out the second part, which is very simple. You have to just substitute the values of time to get the instantaneous value of acceleration and velocity at the various times that is given.
Sir,
Yes.
sir, for the second part, do we have to substitute the value of pi to get a proper numeric value, or just we can leave pi as
You can leave the answer in whatever form. Like if there is some root term coming pi square, you can leave it that way also. It's fine. But the units you understand, right? V will be in meters per second and A will be in meters per second square. Right? It's clear now?
Yes. Yes.
Okay, people. So hope all of you are getting the answers now. So we have to calculate these two quantities at 1, 3, and 6 seconds. So let's look at that calculation next. So we can see that at t equal to 1 second, okay, v will become how much? It will become 10 pi by 3 cos pi by 6. And cos pi by 6 is root 3 by 2. So this will become, so it's 5 pi by root 3 meters per second. And you can see that the direction is positive. Okay, then acceleration at the same time will be minus 5 pi square by 9 sine pi by 6, and sine pi by 6 is half. So the acceleration will be negative in direction and will have a value of, or a magnitude of 5 pi by pi square by 18 in meters per second square. So you can see that at this moment of time, P and A are opposite to each other. At t equal to 3 seconds, your V will become 10 pi by 3 cos pi by 2, means that it's 0. So it's at rest. It comes to rest for a moment. Okay? And it's understandable because your V was positive, but A was negative before that. So it was slowing down. At a certain instant, it must have come to rest, and that instant this is showing us is 3 seconds. Now cos pi is minus 1. So now V is becoming negative. And that's also understandable because at this moment it had come to rest at 3 seconds, but it continued to have a negative acceleration. So that means this negative acceleration would have pushed it in the negative direction now. Sine pi is 0. So acceleration is 0 at this moment. Yeah, so the thing is that, see, if your velocity at some instant is not zero, but after some time it is becoming zero, that means the object is decelerating. So it should have an opposite direction of acceleration. If the direction of acceleration is the same as the direction of velocity, then how the velocity will become zero? Because you're understanding the point. No?
Yes, sir.
Okay. Now we will come to that special case of, actually before that, one more thing. The relation between acceleration A and dv by dx. Okay, now this might seem a strange thing right now, but when I explain it, it will become clear what we mean by this. Okay, so acceleration by definition is dv by dt. Now, if we use chain rule here, we can say that dv by dt is equal to dv by dx into dx by dt. Say this, okay? This is basically the basic statement of chain rule, that dy by dx can be expressed as rate of change of y with respect to some other variable into rate of change of that variable with respect to that application over here. Okay. So now dx by dt is nothing but the instantaneous velocity. So acceleration, which is dv by dt, can also be expressed as dv by dx into v. So this is the relation that it has. So this is an additional mathematical relation. So this is the relation of A with dv by dx. This one. Okay. Or we can say that A is equal to v dv by ds using the same relation. So we will see the application of this also when we come to the numerical problem solving part. Okay. But this is just to understand over here how we can make use of chain rule to find out the relation between acceleration and dv by ds or dv by dx, as may be the case. Now let's move on to a special case of 1D motion. That is uniformly accelerated. motion along a straight line. So not only it is one dimensional, but it's one dimensional in such a way that the acceleration is uniform. So the rate of change of velocity is uniform. So that is what the statement implies. So that means the rate of change of velocity A is a constant. So if initial velocity equals to u at time t equal to 0, then we can integrate it in this way by making use of definite integration. Like we learned earlier, at t equal to 0, the value of v is equal to u, and at time t equal to t, the value of v is okay. So the lower limit is the initial condition. T equal to 0, v is equal to u. The upper limit is the instantaneous value. At the instantaneous time t. Okay. Now, next is when we execute this integration, it becomes something even simpler than what we've seen before. Because the A is a constant this time. So it just comes outside. And we are left with this extremely simple integration. On the left hand side, we have V going from U to V. On the right hand side, we have AT going from 0 to T. Comes V minus U is equal to AT. So we get the equation that you're very familiar with, but we get its proof from integration. So again, this kind of integration has been used here, that integration of dx is x plus c. So integration of dx from, let's say, a to b will become x from a to b. So that is b minus a. So this type of definite integration has been used in both the left hand side and the right hand side. Small a is just a constant here. Unnati, I will come back to your question better. Okay, I saw the question only just now. Sorry. Okay. I will take you back to that previous question and explain the answer to that question. Just note down this derivation first. Okay. So as you know, this is called the first equation of motion for uniform acceleration. There are three such equations. So this is the first of the three equations. Equation number 1. It is giving us the instantaneous velocity v as a function of time. So it's a velocity time relation in this special case when the acceleration is uniform for a straight line motion. Yeah, so sorry, I had got disconnected. So let's get back to this. Okay. Yeah, so just going back to the earlier section for just a moment. Yeah, so Unnati, can you send me your question again? I lost that message because I got disconnected. Oh wait, I have the message. Yeah. So at first we take pi by 6 and then pi by 2. So can take any radian value to substitute. No, the thing is, see, we are substituting the value of t over there. Okay. So the important thing is velocity as a function of time. No? So v is as a function of time as this. So for example, when we are calculating the instantaneous value of v at t equal to 1 second, okay, we will substitute the value of t as 1 second. So it will become 10 pi by 3 cos pi by 6 into 1. So it will be this. When we are substituting for t equal to, let's say, 2 seconds, we'll substitute t inside that bracket as 2 seconds. So it's pi by 6 into 2. So that's how that's becoming pi by 3. So like that. Hope this point is clear now. Okay, good. Okay. Check. Also, I guess you would have finished understanding and writing this derivation. V as a function of time. In the special case when acceleration is uniform, how we get this relation that V is equal to U plus AT. Okay. So this is the integration way of deriving this equation, or the calculus way of deriving this equation. Okay. But also we can make a much more simple justification of this. We can see that here dV by dt, which is A, is uniform. So it has a uniform rate of change. That uniform rate of change will be such that the average rate of change is equal to the instantaneous rate of change. So we can say that V minus U upon T minus 0 is equal to A. So from that, so we can alternately define it this way also. Because it's a very simple case. The rate of change is uniform. So we need not have done the integration also. We could have just justified V equal to U plus AT equation by using this. Okay. Now, next thing, we want to find the displacement as a function of time. So that is where our application of calculus becomes compulsory. Okay. So now, next, since B is equal to ds by dt, okay. So here ds by dt is U plus AT. Obviously, we understand here that U and A are both constants. Because U is the value of the initial velocity. It is not a variable, it is a value now, which is constant. Okay. Whereas A is the uniform acceleration. Therefore, U and A are both constants. So when we integrate this now, we can integrate this from 0 to S while the time is changing from 0 to T. Left hand side will become S from 0 to S. Right hand side become ut plus half at square from 0 to T. The integration of u plus at dt, like so that's yeah, and then I'm putting limits, so I'm removing the constant. It's like integration of that kind of thing. this becomes our second equation of motion. Where we are getting displacement s as a function of time. This. Okay, now let's move to the third and last equation. Let's see how we'll get that. So if you recall, acceleration, which is written as dv by dt, can also be written as dv by ds into ds by dt, which makes it dv by ds into v. So acceleration, which is v dv by ds, is uniform over here. So if you cross multiply this now, get like this, okay, where v is instantaneous velocity, okay, s is instantaneous displacement, that is, it is displacement from t equal to 0 to t equal to t. This is velocity at time t equal to t. But a, that is the uniform acceleration. So integrating this on both sides, because a is a constant, so it will come out. So at t equal to 0, the initial velocity was u, and at some time t, the instantaneous value of velocity is some p. So displacement goes from 0 to s as your velocity goes from u to v. This time on the left hand side, the integration of v dv is v square by 2. On that we have to put the limits u to v. On the right hand side, the integration of ds is s, and on that we have to put the limits 0 to s. So here we are using this kind of integration, that we have integration x dx, that's x square by 2 plus c. So we have the integration of x dx from a to b, that is equal to x square by 2 raised to the limits a to b. So that will become b square minus a square by 2. So we'll use this integration next. Okay. So left hand side will be v square minus u square by 2. Right hand side will be as. Okay. And now rearranging these terms, you will see that you'll get v square minus u square is 2as, or we get the standard third equation. The relationship between instantaneous velocity v and instantaneous displacement s. So again, you can see it's all an application of calculus. In fact, here it is an application of chain rule first and then integration. This is equation 3, which is the relation.
So it is just for our understanding, the derivation.
Yes. Okay. Yeah, I mean, it's part of your syllabus also that you should be able to execute the derivation. But yeah, in problems, we will be using the equations directly, right? In numerical problems, we will not be doing the derivation, we'll be using the formula directly. Okay? But it's equally important to understand where the formula has come from, understand the process. Okay? So this is the relation between V and S. In the above equation, U and A are constants. The variables are V and S. Okay, so people, with that we complete this session today. Okay, you can start doing questions from the module. I will send you a list of questions plus a worksheet also. Okay. Now I just want to briefly talk about some additional reference books also before we complete today's session. So in physics, some additional reference books that you can use now that you've completed vectors and calculus. So you can use this book called Concepts of Physics. Comes in 2 parts. By Dr. H.C. Verma. So use this for numerical problems in the form of the solved examples that are given in it and objective and subjective exercises. So numerical problems of JEE Mains plus advanced level. Second is you can use this book, Fundamentals of Physics. Again, parts 1 and 2. So in 11th, you will need only part 1, but it's better if you get hold of both the parts because you'll get it at a discounted rate and you'll need it for 11, 12 put together. So this is by authors Robert Resnick, David Halliday, and Crane. This is by Wiley Eastern Publications. So use this for theory reading only. Okay. Don't do the numerical problems in this because it's very basic level, formula based kind of thing. But for detailed analysis of theory and definitions and reading, this is a very good book. Alternately, you can also use NCERT. Doesn't matter whether you're in HSC or ISC or CBSE, NCERT textbook is very good for theory reading. But preferable is Resnick, Halliday, Crane. And one more book that you can use for additional problem solving is Physics for JEE Mains plus Advanced series. There are actually 5 books in this series. Mechanics 1 and 2. Waves and Thermodynamics. Electricity and Magnetism. And Optics and Modern Physics. The entire 11-12 syllabus is contained in these 5 volumes in this. Okay. This is by T.C. Pandey, Arihant Publications. So So you can use this book for additional revision problems. So from this point onwards, from kinematics chapter onwards, you can start referring to these reference books, and many a time in class we will be discussing some of the questions, particularly from H.C. Verma also. Resting holiday you can use for theory reading yourself in your like self-study time. But as you're reading that theory, if any questions come up and any doubts are there, you can keep them noted and discuss with me during the mentorship sessions or during the lectures. Yeah, again, HC Verma is for both 11th and 12th, series 1 and 2. I mean, parts 1 and 2. Okay. Anyhow, so that's it for today's session, people. Wish you all the best. Have a nice day. Enjoy the monsoon weather.
Bye, sir.
Yes,
Thank you.
sir. Bye, sir.
Bye, people. Bye.
Bye, sir. Thank